All right, class, in chapter 4, we're going to be looking at representing, we're going to be focusing on linear functions. So representing a linear function in function notation, we've talked about function notation already, and it's really looking at this form of f of x, right? Last week we discussed how function notation works, and so now we're going to take a deeper look at linear equations and looking at them from a perspective of linear functions. One example of a function notation is an equation written with slope-intercept form, and that's what this is right here. This is our slope-intercept form. And if you remember, m is our slope, while b is our y-intercept. I also want you to think of b as being your initial point, your initial value, where x is the input value and m is the rate of change, right? And so again, slope is rate of change. And then we have our initial value of the dependent variable, which is our b. Let's look at a couple of examples. So given the following function, complete the table that shows the correct values for f of x. So if I have the function f of x is equal to 4x plus 1, I'm trying to find the y values or the output values, right? So this is our f of x values. So we're just going to go ahead and plug in 4 times 0 plus 1. This gives us 1. And so then f of 1 is going to be 4 times 1 plus 1, which gives us 5. F of 2 would then be 4 times 2 plus 1, which gives us 9. And so that's how we evaluate the functions, linear functions. This should be a review so far. Consider the table of values below. Find the linear function f of x. So now we're going backwards. We're trying to find f of x. So note that the linear function looks like this. F of x equals mx plus b, where m is our rate of change or our slope. So we'll think of that as our delta y over our delta x. And then b is our initial value. So this is really the initial value when x is equal to 0. So that's something to consider, because if this started like at -1, I don't want you to think that that's the initial value. We're looking specifically when x equals 0. So notice here we have x is equal to 0, so this becomes our initial value, or this becomes our b. So now we're left to find the rate of change. Well, the rate of change is just our delta y over delta x. So delta y, you can pick any of these values. So let's go ahead and pick 2 and 8. So I'm going to take 8 minus 2, right? And then I'm going to do 2 minus 1. 8 minus 2 is 6, and then 2 minus 1 is 1. So our rate of change is 6. One thing to note is that since this is a linear function, right, then we're going to have a constant rate of change. So let's just double check that that's the case. So if I look from 0 to 1, this is a change of 1, this is a change of 1, and this is a change of 1. When I look at these differences, -4 to 2, that's going to be a change of 6. From 2 to 8, that's a change of 6. And from 8 to 14, that's a change of 6. So our rate of change, again, is going to be that delta y over delta x. And so we can see that it's constant at 6 over 1. So now that we have our rate of change and our initial value, so let's go ahead and plug this in. So we have f of x is equal to our rate of change, which we said was 6. Here's our independent variable x, and now that's going to be -4. And remember that -4 came from the fact of what does a function equal when x equals 0. Okay. Calculating the slope. So again, that's just that rate of change. We just talked about that, right? Here's our delta y over delta x. It's our rise over run. Okay. All right, so let's look at an example. If f of x is a linear function and 2, 3, and 4, 0 are points on the lines, find the slope Is this function increasing or decreasing? So we talked about increasing and decreasing functions already. So let's find our slope, our m, or our rate of change. So delta y over delta x. So y is going to be 4 minus 3 all over 0 minus 2. 4 minus 3 is 1, and 0 minus 2 is negative 2. So we have a slope of negative 1/2. All right, so is this function increasing or decreasing? Since our slope is negative, this means that we are going to be coming down and over, right? So this is telling us that we have a decreasing function since our slope is negative. Okay, so that negative slope is what's telling us that it's decreasing. So that means if I were to draw a quick graph here, my function here, this linear function, should look like something like this. So remember, and we talked about, like, if I wrote hope going down, it is in fact going downward, so it's going to be a negative slope. So we do have a decreasing function here. All right, the population of a small town increased from 1,442 to 1,868 between 2009 and 2012. Find the change of the population per year if we assume the change was constant. So because we're trying to find the population change and assuming it's constant, this is a big indication that we are looking for the slope. So we are trying to find a rate of change or a slope, right? So this is going to be our delta y over delta x. So now we need to think, okay, well, what is x and what is y? Remember, x is going to be our independent variable. And so our independent variable is going to be the years, right? The years are not depending on the town's population, but the town's population is depending on the years. So we can see that from here, we have 2 points. I have 2009, comma. So in 2009, we had a population of 1,442. And in 2012, we had a population of 1,868. So we're going to subtract the populations of 1,868 minus 1,442 all over 2009. Oops, I wrote this backwards. 2012, sorry. Minus 2009. All right, so let's go ahead and do the subtraction. So if I take 1868 and I subtract 1442, I end up with 6, 2, 4. So 426 divided by, and now 2012 minus 2009, that's going to be a difference of 3 years. Okay, so I end up with 426 divided by 3. So my rate of change is going to be 142. Check me on that. I just did that in my head. But this is going to be my rate of change is going to be 142. But now, because our problem was in words, our answer should be in words. So what does this mean? This means that the population is increasing at a rate of 142 people per year. Okay. All right. Example 3 here. The population of a certain town is increasing linearly each year. The population at time t is 4, is 1,580, and at time t is 7 is 2,000, where t is the number of years after 1997. Find P of t, the equation that represents the population at a time t. All right, so here we're going to look for P of t. So remember, P of t is going to be composed of m times t plus our b. Remember, we need to find out what our rate of change is and what our initial value is. So let's calculate the rate of change. So our rate of change is going to be the delta over delta x. So we're going to have 2,000 minus 1580 all over. And then this is going to be 7 minus 4. Well, 2,000 minus 1580 is 420 divided by 3. And so this looks like our rate of change is going to be 14. $140. So that's our rate of change. And so now it says, but we need to figure out what that B value is. What is that initial value? So in this particular case, notice that T is equal to 4 is 1580. So it's not sufficient for me to say, well, this is the 140 is going to be the start, or that 1580 is going to be the start. We actually have to plug it in. So let's go ahead. So we have P of T is equal to 140T plus B. So I'm going to pick one of the values. Let's go ahead and pick 7 and 2,000. So I have 2,000 is equal to 140 times 7 plus B. All right, so 140 times 7 is going to be 980. And then we have 2,000 on this side. I'm going to go ahead and subtract 980 from both sides. And so 980, or 2,000 minus 980 is going to give us 1,020 is B. All right, so then that means that our function P of T would be P of T is equal to 140 T plus 10,020. So this is telling us this 10,020, this is the population in the year 1990. Okay, so it's good. It's always important to note what T represents. So it's the years since 19 or after 1990. So 1,020 would be the population in 1990. All right, example 4. So for example 4, Emily is spending money at constant rate. Suppose she initially has 1,100. After 5 months, she has 800. Find the rate at which Emily's amount of money is changing. So we have her initial amount. So this is when, for instance, x is equal to 0. We have 1,100. And then when x equals 5, we're going to say that x is the number of months. And so after 5 months, it's 800. So we can see that there is a decrease. So we are looking for a rate of change. So this is going to be our delta y over our delta x. And our delta y is going to look like 800 minus 1,100 over 5 minus 0. So this is going to look like 300 over 5. And this is negative, so this is going to equal negative 60. So this looks like Emily's amount, so it looks like she is decreasing. So every month Emily's amount of money is decreasing $60. Okay. All right, that's it for this video. I'll continue the next video with writing and interpreting equations.